In section 4.5, we're going to look at a few application problems. These will be exponential growth or exponential decay, and we'll actually take a look at, although I'm not sure if it's going to show up in any of your problems, you will be exposed to a new kind of model called logistic. All right, this is pretty obviously a growth model. This is a decay model. In both of these, if you look back up here, they both have a base E, which is greater than 1. So it seems like they ought to both be increasing or growth models. But it goes on to explain that there is a coefficient in the exponent, and if the coefficient is positive and the base is greater than 1, it's increasing. But if the base is greater than 1, but the coefficient of the exponent is less than 0, in other words, a negative exponent. Remember that negative exponent means 1 over, so you get a fractional base actually, and so it is decreasing. We're going to use our graphers a lot. There is another kind of a growth model called logistic, and we're not going to spend really much time with this, but it is a model where there is increasing for a period of time, and then it switches its curvature, which would be a change in inflection, and it becomes a decay curve, and there is a horizontal, it's not a decay curve, but it does slope down, and it hits a ceiling. So when it changes its curvature, and I misspoke when I said increasing and decreasing, this does have a characteristic you would talk about in calculus. It is concave up, switching to concave down. Nevertheless, the entire time it is growing. We may or may not see these models in our problems. Let's look at our first one, and I will be using the grapher. The first one says an exponential model describes population. Okay, A is equal to 106.3 e to the 0.012 t, where A is the population in millions. We will, in our grapher, change this to letter Y. It also has T is years after 2003, and we will change that in our graphing model to to X. Use the model to determine the population in 2003. Okay, you are given that the time, which is X, is 2003. All right, let's go to our grapher. Let's go to Y equals. Go up. Whoops, I was already where I needed to be. Clear, and type in 106.3 second of the ln key to get e to the 0.012, changing the variable to x. I will come down and clear that out because I don't need it. If you are given an x and you are asked to find the population, which is y, given an x, find a y, you're going to use table. If you want to do it algebraically, you can. So I will do second table, and 2003, I don't type in 2003. X3, this is actually the year, and I want to know how many years it is since 2003. So X is actually 0. So you have to be careful. T is the years after 2003. So you have to take your year minus 2003 to actually get X. So back to the grapher. The top entry is the answer because there's 0. It is, so given that X is 0, the Y value, the population, is 106.3, and then it would be million, but that's already indicated. So all you have to type in is 106.3. Let's look at number 2. We have a different model. We have A is equal to 84.7 e to the 0.024 t, where A, which I will call Y, is the population, and yes, it is in millions, and then T is years since 2003. So we're going to take the given year and we're going to subtract 2003, and we're going to get our X value. So what does this one say? The population of the country will be 134 million in, and it wants a year. It wants a calendar year. So in this one, you are given Y, which is a population, is 134 million, and you're asked to find the year. We will get a T value first, and then we will figure out, or we will get an X, but we're going to have to then put it on the calendar. We'll have to add 2003 to it. We'll demonstrate that. All right, back to the Y equals. A growth function. Let's see. I'll clear this out. This is 84.7 second, my e to the 0.024 variable x, and I have another y value, so I type it in, 134. I'm going to go to my window. I'm not sure how far my x's need to go. Well, I have -1 to 20. The y's, you need to see the horizontal line you're going to put in, which is at 134. So let's just look at slightly above it, 150. There goes the growth curve. And there is the 134. I barely see it, but it is enough. Second, calc, choice number 5. Head over to it. You can travel on either the blue or the red using the up and down arrows to toggle if you want to. You just need to get close and then enter, enter, enter. You get 19.11, I think it was. Well, this is how many years since 2003. So if we had 2003 and we went 19 years, because I don't really care about the decimal, we would have 2022. And this is the year since 2003. You have to almost use your common sense when you're going to subtract 2003 and when you're going to add 2003. When you're looking for how many years, you will subtract 2003 from your calendar year. But if you know how many years, you add it to 2003. So that was 2022. All right, the next one It actually is a decay curve, and how can I tell that? Well, two things. It says it, and the exponent is negative, which would mean you're going to have a 1 over. So this model is A equals 16 e to the negative 0.000121 t, where, let's see, after t years, they do not ever mention anything about after a certain year. So I will use Y, which will be the amount carbon. I'm sorry, I did not read out loud. This model describes the amount of carbon-14 present after T years. Use the model to determine how many grams of carbon-14 will be present in 5,679 years. Okay, so Y is the amount of carbon. T, which I will call X, is the time since the radioactive substance existed. All right, and when a radioactive substance exists, it decays into this carbon. So I have Y is equal to 16e to the negative 0.000121x, and you are given x is 5679. So I will go to my calculator, go to the y equals, clear that out, type in 16 second ln negative 0.000121x. If I'm given an x and I'm finding a y, I go to table, second table, and I'm going to delete these. Well, I was going to. I'm going to type in 5679. That's the number of years, how much carbon will exist, and the instructions say round to the nearest whole number. 8 grams will exist. This was a given an x, find y. All right, last one. We have prehistoric cave paintings in France, and the painting contained 13% of the original carbon-14. Use the exponential decay model to estimate the age of the painting. So I'm going to go ahead and do my variable changes. A, which is y, is equal to A sub 0 is the original amount, and although it doesn't say it, this refers back to number 3, and there were 16 grams to start with. All right, so this is 16 e to the negative 0.000121x. What are they giving us? They're giving us the amount. It is 13% is left. Since we only have 13% of this left, then this amount is 13% of 16. All right, I had a little technical trouble. I'm not sure if this recording is going to come out very well, but we do have our function with x related to the time, or the age of whatever the painting is or whatever the artifact. And we put 16 in the place of a sub 0, which is the original amount that I got from problem number 3. Now, it wants to know what is the age of the painting. In other words, what is X when Y is 13% of the original, so 13% of 16. Well, 13% written as the decimal, 0.13 times 16 is 2.08. So we're saying what is X when Y is 2.08. So I will put this as Y1, and then, oh goodness, I just had a cat decide to jump on my computer. Hold on. So I will have Y2 be 2.08. Now the issue may be finding an adequate window. Let's see. I believe that when I quit working on this recording, I was looking at this particular window. Let me go back in and see. So there's my 2.08. There's that. My window with X being the number of years. That may need to be huge. In our previous problem, I think we had close to 6,000, and it was just down to 8, I guess it was grams, of the carbon-14, and so I'm trying to get it down to 2.08. So I'm going to look and see what 10,000 does for us. All right, there's the decay curve, the amount of carbon-14 declining. There is the 2.08, and they don't intersect within this window, so I'll go back to window, and I will choose the X's to be, let's say, 20,000. So I'm going to see more in the horizontal direction of my decay, and now when I have the 2.08, I do see an intersection, so second, calc, intersect, go toward the intersection. All right, that'll do. Enter, enter, enter. It looks like I have an answer of 16,861 years. All right, so back over here, under these conditions, I will find an X, which is 16,861 years. All right. So we are done with our application problems, and we did focus on using the grapher in these problems.